Hello, everyone. I am Shashank Agrawal. I am a research manager at Coinbase and also a research partner at Delendum Ventures. About a month ago, we organized our first event on programming languages in ZK, and it was a big success. Today, we have our second event, Compiler and Composability in Zero-Knowledge Proofs. And we have a great lineup of speakers for you today. We have Bobbin Threadbare, founder of Polygon, Maiden. We have Brian Retford, who is a co-founder and CEO of RISC-0. We have Izaak Meckler, CTO of O1 Labs, and Albert Rubio, who is a professor at UCM and also a Circom development leader. So the agenda for today is that we have 60 minutes for the talks. So every speaker gets between 10 and 15 minutes to present their material. And if we have time, we can also take a few questions. Then there's going to be a discussion panel, and we'll have 2 more people join us for the panel. And towards the end, if we have time, we can do a bit more Q&A. If you have questions during the talk, you can share them on the Telegram group or on the Zoom chat, or you can also just send it to me, whatever works for you. Okay, so let's get started. First up, we have Bobbin. Bobbin, you can share your slides.
Yeah, hello everyone. Very excited to be here. Thank you for having me. Yeah, let me share my slides and I'll get started. Can you guys see the screen?
Yep.
All right, awesome. So my talk today is going to be about how do you provide program source code to ZK virtual machines, and given the time constraints, it's going to be fairly high level, but hopefully it still will be very interesting. Before I go into specifics of how do we provide programs to ZK virtual machines, I want to kind of set the context. So first, let's think about all the computations and how we can represent them. There is really, at a high level, 2 ways to think about the computation. You have a circuit computation, and a lot of ZK systems work in a circuit model where you design a circuit, and then basically the way the computation works is a signal propagates through this network of gates, and you get some outputs at the end. In the context of ZK, these are not actual physical circuits. These are like algebraic circuits, but that's how it works. And then the second approach is a machine computation. And this is basically you have a computation state, and then you apply a transition function to that state, and that state changes with each kind of application of a transition function. And these are just different ways to, like, any computation can be represented in either a circuit model or a machine kind of model. There is difference in like which computations could be done more efficiently. So, for example, if your computation has a lot of repeated structure, a machine computation is the more efficient way to represent it, because the transition function can be pretty small, and then you can represent the computation very efficiently like that. If your computation does not have a lot of repeating structure, circuit computation is probably best. In the context of virtual machines or ZK virtual machines, the machine computation is the more efficient, because in a virtual machine is basically application of the same kind of transition function. Even a regular CPU is basically it is a machine computation where you have like let's say a set of registers, and you apply some transition function to the registers, and they change their state from one cycle to the next. But each cycle is described by a fairly maybe not fairly, but relatively simple transition function. Much simpler than the computation that is possible to do. So I will be focusing on this machine computations because this is what is kind of relevant to ZK virtual machines. And also because I'm focusing on this is going to be more kind of focused on Stark proving system, because this is, the machine computation is a very natural fit for a Stark proving system or specifically air arithmetization, where you can describe a computation using this, what we call algebraic intermediate representation that is used in many Starks. All right, so with that context, what is the ZK virtual machine? And to start out with just what is a regular virtual machine. So as I mentioned, this is kind of like a machine computation, whether you have some initial state, you have a transition function that is usually described by a program, well, a transition function is actually described by the VM itself or the logic of the VM itself. And then you execute the program which applies this transition function many times, and you can get a final state. So that's how we can think about just a regular virtual machine. And then in a ZK context, we get a few more things here. So the first one is there is a proof that gets generated that proves that this transition, that the program was applied correctly to this initial and final state. In our context, we usually want the proof to be fast to verify. And then you also get this witness, something that you can provide non-deterministically, or I guess it's a secret input that could be fed into the VM that doesn't need to be shared with a verifier, for example, to verify that the program was executed correctly. So this is something, let's say if you're verifying a signature, VM can verify a signature, but you don't necessarily need to share the signature with someone else. Someone else can say, okay, there was a signature against this public key and against this message. And the proof proves that the prover knew that signature, but the signature was provided through the witness. So we don't really need to know what the signature was. So this witness needs to be known only to the prover. So with this context, I basically want to focus today on how do you provide programs to the virtual machines, because there are a number of ways to do it. And not to say that this is a fully exhaustive list, but there is, I think these are the major approaches that I can think of. So the first approach, and I'll go in more detail on each of them, but the first approach is to provide the program through what we call public memory. So you can basically initialize the memory of the VM with some program, and then you can execute the instructions of that program one after another, and according to the logic of the VM. The other approach is something that is called bootloading, and this is where you provide a hash of the program via public inputs, but you provide the actual program non-deterministically through this witness, and then within the VM you unhash it, kind of like an you invert the hash and populate the memory of the VM through that process, and then you start executing the program. The other approach is to do a code word commitment, and basically what this means is that it's also kind of like you're doing it through a public input, but you compute a separate, in the context of a start specifically, where you do this, extensions, for example, you take like a polynomial and then you extend it. So like the code word in this case would be like an extended polynomial. So you take the instructions, you compute this code word commitment, and you include this commitment into the proof itself. And then anybody can, there is also like a mechanics within the VM that verifies that this commitment to the code, to the program is the same as the one that was used in the main kind of execution trace of the VM. And then the last one that I want to kind of cover in this talk is using a Merkleized abstract syntax tree. This is actually what we use in Polygon Maidan, where you provide the root of this program, which is encoded as in a structured way, and the VM itself decodes this. You provide the actual program non-deterministically, similar to a bootloading approach, and then the VM decodes the program and executes it. So to go into a bit more detail on each of this, so for the public memory, so let's say we have a set of instructions that we want to execute. Within the VM, assuming that the VM has a memory, you would have like a set of, let's say the first n slots of memory would be initialized with this set of instructions, and then within the VM you also have a program counter that when the VM executes it moves the pointer to a specific instruction that is being executed within the memory. Again, there is a bunch more mechanics here which I'm skipping over, but at the high level these are the main components of how you would provide program into the public memory. And then for public memory, you use kind of like a permutation. You can use like a float-like permutation argument of how you represent public memory. It's actually a fairly, there is a very efficient way to do it, or relatively efficient way to do it. With a bootloader, the approach is slightly different. So you still have the instructions and you have the program. Now you have a hash of this program. So you can imagine that you've computed the hash of the program by just linearly hashing the instructions. You provide the hash of the program as public inputs, and you provide the actual instructions as a witness. And then you have this bootloader, which could be maybe hard coded into the VM, or could be provided as a, for example, another public input. So I kind of omitting that detail. But it's like a mini program that basically takes the instructions and hashes them within the VM, and then makes sure that the kind of like the memory that you non-deterministically initialized within the VM is equal to the program hash. So you basically invert the hash within the VM. And then once the bootloader is done, your memory is initialized to whatever it needs to be initialized within the VM. You do the same thing as in the previous approach, where you have a program counter that now goes from one instruction to another as the VM executes those instructions. Yeah, so this is like the bootloader approach. The other approach is via code word. So you still start with the same set of instructions, and you provide those instructions, you can say, as a witness. I mean, maybe kind of technically not necessarily as a witness, but for our purpose, you don't need to share the instructions with the verifier themselves. So I put them as a witness. And then you have this read-only memory within the VM. So this is not something that is being unhashed or can be modified, but you basically fix the program as a set of read-only locations. And then there is actually, you're going to do like a permutation type check between this read-only memory and the main kind of trace of the VM that will make sure that you're executing the expected program. And then you have the program counter, which kind of points to this ROM and is able to execute instructions in a manner similar to before. There is one extra component here, is that this code word, you kind of take these instructions, compute their code word, or extend the polynomials, and you can you include the commitment to this code word into the proof. And this could be done as a for those who know a little bit about Stark proofs, is that you have different Merkle roots committing to different parts. Like there is a Merkle root that commits to a main execution trace, but this code word could be like a different Merkle tree, or represented by a Merkle root. So you will add another Merkle tree to the proof, and that code word would be included there. There is, again, a bit more complexity here, because you need to include several columns in that commitment. And then in the main trace, you need to include the mask that allows you to kind of like execute multiple instructions, like if you have loops, something like that. So there is, again, skipping over some of the complexity here, but that's a general idea. And then the last approach is using a mask. So a mask, also everything starts out with the same sequence of instructions, and then you have the program root, and I'll cover in a couple of seconds what the program root is. But basically, you provide this program root to the VM, and the instructions go as a witness, and program root goes as a public input. And then you have this component within the VM that is responsible for decoding the sequence of instructions and computing this program root as it executes the instructions. And then the output of this decoder is a sequence of instructions that needs to be executed on the VM. So those are kind of like at the high level 4 approaches. And I think to give a little bit more detail about what is masked. So I call this a Merkleized abstract syntax tree. And kind of some of the properties are listed below, but the high level concept of this is that you represent the instructions kind of as a tree, where internal nodes in the tree control the kind of control flow, like whether it is a conditional execution or whether it is like an iterative execution via a loop. So that is all controlled by internal nodes, and the leaf nodes are just linear sequences of instructions that don't have any control flow in them. And to make this a little bit more concrete, like let's say this is our program. It has some instructions, then it has like some if else statement, where one branch has another sequence of instructions, another branch has another sequence of instructions, and then you have some other instructions in the end. And the mask of this program would look something like this. So we have for example, a split block means that you execute either one or the other branch, and the join block means that you execute both branches. So like in this, for example, you start out executing first, you execute this linear sequence of instructions. This sequence gets joined with the if kind of block, and then here you execute either instructions in a kind of true branch or in a false branch, depending on, for example, what if the condition is meant here. The context is like a stack-based machine, for example, and you can check the value in the top of the stack. And then you do the same thing, like going up the tree, and you can compute the root of the tree. And so this root would be represent kind of commitment to the entire program. But unlike a linear hash, it is actually like a more structured Merkleized hash, where you can go to a specific node and see what was executed. So those are different approaches I kind of described, but like, why do we bother, and like, what are the reasons for using one versus the other? So again, I put together a table. It's there are a lot of nuances in this type of table. So like, it may not be accurate in all cases, and I'll try to caveat when what is accurate and what is not. But basically, the things that I would like to kind of like measure this across against is like this prover cost, verifier cost, decoding complexity, and program kind of hiding properties. So, so in terms of a prover cost, public memory is probably one of the lowest one in most cases, because prover doesn't almost need to do anything extra. There is some mechanics in there, but it's very low. For bootloading, prover needs to encode, like actually needs to unhash the program. So like there is hashing that needs to be done within the VM. And for code word, there is also a bit more complexity, because you now have two different parts of the trace and you need to tie them together. And for mask, I would say that prover cost is low, but there is a caveat to that. It depends on the program. So if your overall program is large, but you only execute a small part of it in a given execution, so like there is a lot of different branches, but some of the branches may not end up being taken, the prover cost would be low. But if it is a program where you execute every single instruction, it probably would be actually either in a medium category or maybe even in a high category. And one of the things that I should have mentioned about mask is that it allows you to execute specific branches without like having to like unhash the whole tree. So when you execute a program, you only do specific branches. The other thing is verifier cost. Public memory is fairly expensive, especially for large programs. So if your program is small, it would be fairly easy to for the verifier. But if a program is large, the public memory is expensive. Another approach is because you only provide the commitment to the program, the verifier cost is very low. In terms of decoding complexity, the mask is probably the most complicated one, because you need to compute the hash in a structured way, and there is a lot of mechanics within the VM that is required to compute the root of the program. And the public memory is probably the simplest one in terms of decoding complexity. And in terms of kind of this program hiding, via public memory, you don't actually hide the program. The verifier needs to know the program to verify what's being executed. In terms of the in case of bootloading or code word approach, you can hide a program, but you can hide either full program or you kind of make it public. You can selectively hide parts of the program. And with mask approach, one of the nice properties is that you can selectively kind of like hide parts of the program. You can hide the full program if you want, but you can also say, I'm gonna reveal some leaves in that Merkle tree or some nodes in the Merkle tree, but I'm going to keep the other ones hidden, and that allows you to gives you much more flexibility in terms of which parts of the program you want to make public or private. And one of the nice things about this is, for example, if you have a program with public pre and post conditions, you can reveal those, but what happens in the middle of the program remains hidden. Again, I then went through this very quickly, and then there are a lot of caveats here, so take it with a grain of salt. But this basically covers what I wanted to talk about today. I think I might have gone over time a little bit, but hopefully not by too much.
This was great. Thank you. Very nice presentation. We don't have time for questions right now, but we can take questions later. Let's move on to the second presenter. Yeah, cool. Brian is going to talk about unified compilation framework for zero knowledge.
Hello, everyone. Yeah, thanks to everyone for having me. This talk, let's see, I'm going to try to go through it fast. It's mostly speculative. Can everybody see my screen?
Yes.
Great. Okay. Yeah, so I'm going to talk a bit about what it might look like to think about compilation a bit more holistically through the lens of my experience building compilers for AI accelerators, which is sort of our last company. I wanted to talk really briefly just about what RISC-0 is. I think, based on Bobbin's talk, hopefully people understand, there's a ZKVM is arithmetic circuit that represents an actual, microprocessor that can take instructions via all the stuff Bobbin just went into so eloquently. RISC-0 in particular is a ZKVM that implements the RISC-V instruction set and can thus run, generic programs, things that, so a program written in Rust that gets compiled, say, through LLVM and then into an ELF file, which then gets loaded. We use the public memory model if you're referencing Bobbin's earlier talk. And that works pretty well. However, once you start pulling a lot of libraries in, it's pretty amazing how quickly, load time can take up a lot of your available cycles in a ZKVM. But I didn't really want to talk about all of RISC-0 today. I really kind of wanted to talk about what the sort of patterns in sort of emerging dense computational spaces. So you can think of Bitcoin mining as one of these. You can think of AI especially as one of these, and certainly people think ZK is going to be something like this. This is so how I'm defining this is where you have a workload whose sort of core set of operations is not really that large. It's not general purpose. So in the case of AI, you're mostly doing convolutions and matrix multiplications. In ZK, you sort of have NTTs and elliptic curve operations depending on which proving system you're in. So you have a sort of subset. In the case of Bitcoin mining, you know exactly which algorithm you're running. So the more sort of narrow a particular computational domain is, I'd say the more the more quickly you can sort of run towards ASICs and GPUs. So, CPUs are obviously incredibly general purpose. So, AI took quite a while to get to ASICs and even longer to be able to sort of program them. Bitcoin, honestly went there pretty quickly, in my opinion. And the ASICs were pretty useful because the problem it needs to solve is very simple. I think ZK ASICs are going to be a pretty difficult lift to make generally useful. But I wanted to talk about some of the software challenges that come up when you try to, build software with this sort of evolution of hardware deployment platforms in mind. So the approach that I think started out in the sort of AI realm was NVIDIA would create this library CUDNN, and basically somebody from Python would call TensorFlow and call this do a three-dimensional convolution with these parameters. Now inside something that NVIDIA would ship, CUDNN, there's this huge library. I think it's over a half a gig now of just a million different handwritten or hand optimized, and now mostly computer written, 2 decades later or something, set of kernel library functions that do very specific things based on the exact hardware that you're running on. So to me, and then all of the stuff eventually runs on one specific hardware target. Decisions like this can kind of pollute your framework. So the first version of TensorFlow would pretty much only work with CUDA because it used all of CUDA's memory loading primitives and all this other stuff. So this is why, even to date, you can't really run, AI on AMD cards very well. It's not really a hardware problem at all. It never has been. It's always been a software problem. People have been working on addressing that though. And you're seeing people move to more of a compiler-based approach. And this is what our last startup and open source project, PlaTML, was focused on. And in this approach, your programmer is still predominantly writing in Python and maybe writing through a framework, but underneath that, rather than having this giant dispatch to a vendor provided hardware acceleration library, instead you have a higher level script like JAX or PlaTML or TensorScript. But there are a bunch of examples of these. JAX in particular is becoming quite popular now. And what these languages do, or these EDSLs, is look a lot like the host language, but to really limit the kind of scope of computations you can describe, such that compiler-based approaches are more amenable to actually understanding how to lay out a particular operation on a wide variety of hardware. This comes especially into play when you start looking at ASICs, which we ended up working a lot on once we were acquired by Intel. So the difference between these two sort of approaches is that in the first one, running a single neural network on, say, this, Movidius vision chip that Intel makes could require 50 hand-optimized kernels. And in fact, I had a team of, 200 engineers who would sit there and hand-optimize customer workloads for a particular, very particular use case. So it doesn't really scale at all. The vision of having this kind of higher level description and a compiler is that the developer can just write their program and run it anywhere. So when I look at the sort of landscape of ZK right now, and if you look at the Z Prize competition and the kind of things people are building, it feels a lot to me like the sort of early days of ML and AI. You see like Aleo, amazing work with Leo, but the compilation stack is very custom, very specific to R1CS. And you don't see a lot of the kind of levels of abstraction that will let people easily transition their proving systems to run on different hardware or their customer workloads to run on, say, different proving system. So I think to some extent, the ecosystem is shooting itself a bit in the foot by not sort of embracing a more compiler-like approach earlier. And you certainly see cool examples of people doing this. And Snarkify, this is obviously an example of an EDSL for snarks. So I think the end world that I think we as ZK industry developers can help to, I guess, help ourselves, help the industry, is really trying to figure out how we can let customers, write code as few times as possible and target as many backends as possible, including, our own eventual ASICs if people make them, et cetera, et cetera. So the way that, I think the AI industry is going, as well as a bunch of others, networking chips, et cetera, is by using something called MLIR, which does not stand for machine learning IR. It stands for multi-level IR. And this is effectively the next version of LLVM that's designed to, turn these kind of dense vertical computing spaces into problem spaces that are approachable via compilation techniques. So, I mentioned here, I have heard that, for instance, the Xbox, the most recent one, has at least 10 custom chips in it, and they all have like special compiler stacks based off of MLIR. So what exactly that looks like in a ZK context, it's a bit hard to say, because I think the application level programming primitives are not incredibly obvious. And to some extent, we're trying to run purely general purpose code. However, there are a lot of sort of compiler passes that are probably relevant even to, RISC-0, which runs arbitrary code. Where am I on time? Yeah, there are a bunch of sort of compiler passes that are probably reusable, as well as sort of extending this idea of making EDSLs that can compile to either, code for MIDAN or a specific circuit if it makes sense to accelerate it. So a bit high level there. Happy to talk to people if they're interested in, getting into the nitty gritties of compiler development. But if you're doing any kind of compilation work, I highly recommend you look into MLIR and think about it for its amazing tooling and all the rest of these reasons. And yeah, that's it.
Cool, thank you. Very nice talk. We do have time for maybe 1 or 2 questions, if somebody has questions. If you have questions, you can put them here in the Zoom chat or the Telegram group.
Oh, sorry, because I had a few minutes left. I didn't need to rush through that so quickly.
I mean, if you have something to say about MLIR, you can,
yeah,
take
I mean,
minutes.
Yeah, I can expound upon sort of why people should consider using it. And I can talk a bit about the kind of stuff we're working on in that realm. Specifically right now, we're looking at, RISC-0 has a couple accelerator circuits like the SHA-256 accelerator, and we're working on a bunch of others, as well as, we describe a complete RISC-V chip. So we've been working on a circuit compilation language that looks a lot like an EDSL that lets you describe algorithms and then sort of turn them into circuits that will run in particular proving systems. So we're kind of building up the sort of bottom half of an MLIR-based compiler stack. I don't know how much sense it makes to go as high up as sort of we've gone in the AI world, but I really don't know at this point. It's also true that if you look at, we use LLVM to compile programs for the RISC-V chip, but the chip behaves very differently in a ZK context than it does in a silicon context. Memory loads are effectively free, so any kind of cache management is basically a waste of time. So we haven't really gotten into this, but by sort of investing in an LLVM-based or MLIR-based stack, it's very easy to add and remove certain compilation passes, like cache optimization, for instance, that will result in more performant binaries, as well as giving your customers the ability to kind of understand how to extend and optimize your compilation stack, rather than having something super proprietary, which people ran into in AI a lot, which is, customers wanted to make their workloads more efficient, but there was no way to do that without sort of exposing everything.
See, nice. And also, in the beginning of your talk, you mentioned something called RISC-V ELF. I was wondering what that is.
Oh yeah, so an ELF is just a binary package format for Linux, and RISC-V is just an instruction set. So like any binary you run on Linux is an x86 ELF usually, or an Apple M1 or an ARM ELF. So this is just basically we can run a standard looking binary. Now it's not exactly packaged the same way that it would be for a Linux machine, but it's very similar. So let's see, there are a couple questions in there. A couple use cases of RISC-0. Can the circuits be dynamically formed instead of hardwired for specific circuits defined? Yeah, so I mean, this is similar to what Biden, I always say that Bobbin, because it's Bobbin and Meiden, was describing, ZKVMs, the circuits made once, and you can run any kind of program. So there's a bunch of use cases on RISC-0's webpage if you want to check those out, and in our source repository. One of them is like a hidden information game that's just written in Rust. Do you think there's an opportunity to accelerate workloads on GPUs? Yes, we have GPU accelerated versions of our runtime that are not public.
Cool. Yeah, thank you. I think we should.
Oh, and then transpiling, I think, is garbage, but that's just, we don't have to get into that.
Right, cool. Thank you for answering those questions. Let's get to the next talk. Thank you, Brian. This one is on composability via TypeScript and Recursion, and Izaak Meckler will present.
Cool. Can you guys see?
Yes.
Great.
Yes.
Hey everyone. I'm Izaak. My old title was CTO, now CSO of ON Labs, and I'll be talking about Snarky.js and a few ways that I guess I responded to the theme of composability in compilers. So just to start, I want to lay out what my goals are or our goals, I should say, for a ZK programming system. It should be something easy to learn, easy to develop with. So that means specifically having good IDE, being able to test easily, having good package management, and it should be easy to integrate your ZK part of your application with any other parts of the application that you might have. So for example, like if you're writing a web app, it would be nice if the prover could easily run in the browser or something like that. Or if you're deploying to a blockchain system, that you should have like a smart contract verifier. And also, obviously, it should be performant. So I'll talk a little bit about the landscape just to like situate Snarky.js within this picture. There are bytecode/VM based systems, which we've heard a little bit about now. you could either compile from a new language like Cairo, or compile from an existing language like with RISC-0 or their various EVM-based projects. And then there's circuit-based systems. So this would include things that are like kind of embedded in existing languages, and Snarky.js is an example of something that's a circuit-based system that's embedded in TypeScript for like artworks, or it could be compiled from a new language. And Snarky.js, just to kind of zoom, well, maybe let me go back to that. So as I said, Snarky.js is embedded within TypeScript. Oh, actually, I think I have a slide on this later, never mind. So Snarky.js is a framework for writing zero-knowledge applications, like all of these other ones we've seen. It uses TypeScript. There's no setup or anything. It's based on our Kimchi Snark, which works with these posture curves. It runs very easily in the browser. And importantly, it works well with Mina. So it forms the core of the framework for writing ZK applications on Mina. And if you don't know, Mina is a layer 1 blockchain, which is like based on ZK snarks in some sense. So coming back to kind of my original goals and how this applies to Snarky.js, the goal is to be as easy as possible to get up and running and writing an end user facing ZK app. And in this context, there are many advantages of using TypeScript. So one, like a lot of people know it already. There's no need to learn how to program in a new language, like with Leo or some of these other approaches. You have a solid compiler already with a good type system, very usable, and great tooling already exists. So there's like great editor support in every editor, package management, it's easy to write tests, blah, blah, blah. Also, it very easily runs in the browser or on the server, as you may need. So that kind of ticks all the boxes that we were going for originally. Okay, so this might be kind of a fast talk. I wasn't sure how long to go. A bit about this idea of composability. So for me, what this means is kind of the ability to separate systems into independent, reusable parts. And it's typically accomplished in programming languages via functions and classes. And in Snarky.js, it's accomplished via functions and classes. So pretty similar because you're just using TypeScript. But then also via recursion and proof composition. So this is something that's special about ZK snarks, and as far as actually existing systems, special about Snarky.js. So what does it mean to talk about composability via classes and functions? Basically, you can write classes and functions just as you would in a normal programming language. For example, let's say you want to define Schnorr signatures or some signature scheme generically. You can just define a class for signatures that has some methods on it. So you'll have like a create method that takes a private key and a message and returns a signature, and a verify method that takes a public key and a message and a signature as the self argument or whatever, and returns a Boolean. So that's just the same as how you sort of compose, I guess, in normal programming languages. And usage just looks like calling functions in programming language. Yeah, so the more interesting thing, or more specific to zero knowledge thing, is composability via recursion. So I'm going to use this example of this game called Mastermind. It's a simple game. So the way that works is the following: you have like a secret code master who selects a code word. And that's basically this sequence of colors down here. So we got like green, blue, orange, pink. And the goal of the other player, like the guesser, is to figure out what is the secret code word. And the way that they do that is by sending a guess. So at the top here is their first guess: yellow, yellow, blue, blue. And then the codemaster like sends them back a hint. So in this in this first round, the hint is going to be the single white peg, and that means it's a lot like Wordle. If you played Wordle, that means like one of your colors is correct, but it's in the wrong location. And then the next round, the guesser sends pink, orange, orange, yellow, and they get a red peg and a white peg, and that means one of your colors is correct and in the correct location, and the white peg, that's what the red one means, and the white peg means one, as I said before, one of your colors is correct, but it's in the wrong location, so that would correspond to this pink ball. Yeah, so this is kind of a natural fit for doing a zero knowledge, like for encoding in a computer system with zero knowledge proofs, because you have private information, the secret code word that needs to be held consistent across rounds, and zero knowledge proofs are going to enable us to do that. So let's kind of, oh yeah, so just to kind of explain in code a little bit, we're going to represent the state of the game using just a class. It's going to consist of like the most recent guess, the hash, like a commitment to the solution, and then basically the most recent clue in terms of red pegs and white pegs, and the turn number. But let's go through the flow for how a round of this game would look with using zero knowledge proofs, and we can see kind of how this composition comes into play. The codemaster starts off by committing to their secret solution. Then the guesser will send a guess, so yellow, yellow, blue, blue, and the codemaster responds with a hint. So if you just have them communicating like this, there's nothing keeping this codemaster honest, right? So like the hint here doesn't necessarily have anything to do with the guess or with the solution that they committed to. You want to somehow force them to prove that this hint is the correct hint, given the code word that they committed to and the guess, right? So the way that we do that is basically, oh, sorry, let me just say one thing first. So at the end of this process, they will have played many rounds, and you'll have some final state, right? Which is the guesser won in 6 moves. And this system of this game could be composed inside of a bigger system, which is like a smart contract where they're wagering on the outcome of this game. So in this instance, maybe they wagered, I can win in 6 moves or less. And because he did win, he'll get 100 mina, and the codemaster will have to pay 100 mina. So how would we actually accomplish this system using zero knowledge proofs? How would we actually implement such a system? Well, basically, every time that a message was sent in this interaction between them, we'd also force the player to send a little zero knowledge proof. So this gray box here represents a zero knowledge proof, proving that they're kind of complying with the logic of the game. And at each step, each message will include the proof from the previous state of the game up to that point, and prove, we played the game validly up to this state, and then I'm going to add one more move on top of that and bundle that whole thing up in a proof. So, and you keep going. So each time, each player is proving that they're behaving correctly with respect to the rules of the game, and they are constantly kind of producing this proof that stands in for the play of their whole game. And what this enables is basically this this proof then can be kind of bundled up into one whole proof. So you'll have this for each round of the game, but then ultimately you'll end up with one giant proof. Well, it's not giant, actually, it's the same size as any other proof because it's a ZK star. which summarizes the whole game. It basically says there were two players, they committed to wager 100 mina on the outcome of a mastermind game. They played the game honestly, and at the end, this was the outcome of the game. This player won 100 mina, this player lost 100 mina, and you have this ZK snark attesting to that fact. And now you can go and, if you like, commit that game to the chain and realize the wager. And so this is pretty cool because you were able to, this sort of enables like a kind of horizontal scaling for blockchains where every play of the game doesn't need to be happening on chain. It only concerns these two players, but they can still commit to the game on chain once it's finished and actually execute it. And it's even more kind of composable than that, because if you decide, okay, well, I'm going to be playing a lot of games, and I can't be paying all the transaction fees on Mina. So what I'm going to do instead is run a bunch of games, send those into a ZK rollup, so compress all of those even further into one proof that summarizes all of them, and then you can then like batch commit the outcome of all of these games on chain on Mina. So this facility for recursion makes things extremely flexible. You can compose systems in a really nice and easy way. And in the code, it's super simple. Just to give you a flavor for it, you basically can just take proofs as private inputs, and you just call .verify on them. So here, this is the method for the spy master player who's like sending his hint. There's some other code here, obviously, but basically he just calls like previous proof.verify. And that's like how it checks the state of the game up till that point. And just to kind of say a little bit about like abstracting from this particular example, composability via recursion is really useful for privacy. So if you're in multi-party settings where some party has private data, recursion is an extremely useful and natural like method of achieving that. And also for scalability. So as I said, you get this ability to really efficiently sync state between systems. And that means you can kind of set up your systems in a way that they're as sort of as well distributed as possible. So that's all I got. If you're interested to learn more, please check out the Snarky.js docs. And also this mastermind example is implemented on GitHub.
Thank you. Very nice. Yeah, I'm glad you walked us through an example to nicely explain what you were doing. Pretty cool. Thank you. We don't have time for questions right now, so we will move on to the next talk. Albert Rubio will present Circom 2.0 Scalable Circuit Compiler. Please go ahead. I think you're on mute.
Okay. So
okay, much better.
No, it's fine. So first of all, thank you for inviting me to this event. So I will speak about this programming language and compilers. So I will be more on the side of compilers and for particular languages that are DSLs for building circuits. So since I have not much time, I will try to move quickly. So in case you don't know about Circom, then some parts will be not that easy to follow. But in general, the idea is to show that there are special things in compilers for zero knowledge, for languages that create circuits for zero knowledge proofs. So let's go. So when preparing or defining circuits for snarks, what we have to do is to go from some computation to an arithmetic circuit, okay? And then from this, we get these constraints that define the circuit. And on the other hand, we need to also provide a solution for the circuit given the inputs, okay? So just say what's the result of a particular computation. And from this, from the constraints and from this witness, from this result of all the computation, we can send it to this Snark.js tool and get the prover and the verifier. Okay, so that's the schema we follow for producing these ZK proofs. And then in this context, we need a language to define these circuits, and also a good compiler to produce these constraints and the code that is gonna produce this witness. So this is what Circom is. So it's a language to write these arithmetic circuits and a compiler that produce this. Okay, so Circom is a DSL created by Jordi Bailina quite long ago and it's part of this Eden 3 project for identity, sovereign identity. So Circom 2 is the new version of this compiler, which is mainly developed by our group at UCM. And the Circom compiler is open source and fully written in Rust. Okay, and the main difference with the previous version of the compiler that was written in JavaScript is that it's really faster compared to the other one, and also provides more security because it's written in Rust, and then you can trust more on the compiler. So the good point with Circom is that the community is rapidly growing, and many people is now using Circom for many different purposes. And the community has been crucial for the success of Circom. So they provide improvements or ideas to go, and we are really happy with this community. So the aim of a Circom program is these two things: to provide a symbolic description of the circuit, so really describe the circuit by means of constraints, and also ending up providing an efficient way to compute the witness. So you have to consider these constraints are polynomial constraints. So defining the constraints is not going to give you an efficient way to compute the witness in many cases. Okay, so then you have to provide another way to compute the witness. Okay, and even if you have some control flow in the computation you want to describe, then it's nice if your code gives you a way to describe this flow, but then you have to provide the constraints that also define this control flow. Okay, so the Circom allows the programmer to design arithmetic circuits really at low level. Okay, so it's completely different to other approaches we have seen. So we focus on this low level because at some point you sometimes need this low level depending on your purpose. Okay, so then it's like when you do in electronic circuits. Okay, there are programming languages for defining electronic circuits because sometimes you really need to go to these constraints, to definition of the real circuit. And in Circom, all the constraints, all the part of the circuit have to be explicitly added to the program by the programmer. Okay, and then what the compiler will do later on is probably simplify your constraints, okay, and remove some signals, but we'll never introduce new signals. That's very important. New, let's say, variables of this constraint system. Okay, so in Circom, just let me show you a pair of small examples. So you have things like this. In this case, you're seeing that the output is obtained by the multiplication of these two inputs. And it gives both, gives you the way to compute the output from the input, but also generates this constraint that says that the output is equal to this multiplication of the inputs. So in many cases, this can be done. It's very nice, but there are cases in which you need different ways to describe the computation and the constraints. So you need sometimes to give explicit constraint. It gives only a constraint. It does not give you anything in the computation. It's just a constraint. So it can be simply a computation. You say the output will be obtained by multiplying these two, and this is kind of an assignment in standard languages. And then there is the nice thing with this one, which gives you both. Okay, so in general, we are happy using this, but sometimes we need to combine this and this, because the way to express the constraints cannot be done directly with assignments. Okay, so this is the key thing in Circom. And to see a nice example of this is just imagine that you want to do a circuit that says if an input is 0, okay? So there is a bit of a problem if you really want to produce the constraints, okay? Because of course this is not, this cannot be done. Okay, you see, it's just saying that you have a constraint that says in is equal to 0. This is not a polynomial constraint. This is not a multiplication of anything. Okay, so this cannot be done. And then you can say, well, let's put it like this, because then I just say the output gets this. But then there is no constraint. So there is really a terrible thing, because you're making a circuit without constraints. You will compute a signal output from this, but there is no constraint. So there is no circuit at all. Okay. So this is a circuit that does this. Okay, so there is quite strange, but it is like this. So you need to create this inverse and then say that the output will be the multiplication of the inverse by the input, and also you add this constraint to end up with everything. Okay, this is okay, but so which means that using this does not guarantee the equivalence between the constraint part and the computation part of the witness. Okay, so it's responsibility of the programmer. Okay, so we can have more complex things like this in which we combine components, and so after all we have in some high-level programming language, but this is level with respect to the circuit. Okay, so the circuit should be explicitly defined by the programmer, but this gives a lot of control. Okay, in this case we use this subcomponent, and here we build an expression with the sum of all these input, and after all what we say is that the output will be the result of asking whether the sum minus n was 0. Okay, so we are composing things, but okay, so now let's move to important things in Circom. We have a Circom library of circuits, which is really useful for the users and the programmers, because it has binary transformers, comparator hash functions already implemented, elliptic curves, the sparse Merkle trees. So all these things are already given. So you build on top of this. So you don't need, in many cases, to go really to so low level things. But if you want, you can. So if you are creating a new circuit which no one else has implemented, so you have to go there inside to the constraints. Okay, so the part of the compiler is that in some cases there are arithmetic circuits, okay, that generate really hundreds of millions of constraints, and this can be a real problem, because in general you cannot handle such an incredible amount of constraints, and many of those constraints can usually be eliminated. Okay, so this means simplifying these systems. Okay, so for instance, in some in the SNARKs, normally you cannot go beyond these 2 to the power of 27 constraints. Okay, so for instance, in some rollups, you can get these numbers. Okay, so you need to simplify and remove constraints a lot. Okay, so we remove constraints and we simplify constraints without modifying the behavior of the circuit. Okay, so just to show you a little bit. So in the previous one, we had these kind of constraints. So we will remove these two, which are what we call linear. Okay, so they're just addition of signals. So we can remove all these constraints. I'm not going to enter in the details of how it goes, but we can do it. But imagine if you have to do this for hundreds of millions of constraints, you have to do it well, okay? Because otherwise it takes a while. So the compiler applies this clustering and parization of the simplification, applying let's say a good version of this Gauss-Jordan elimination, and iterates the process until no linear constraints are left. Okay, so we have a compiler that can reduce sometimes 80% of the constraints, because many of them are linear. Okay, so we can remove all them. So look at the figures here. Okay, you see, so we can have very large circuits that need this amount of local memory to be simplified. Okay, so then swapping is needed, and this slows a lot the process. But we can reduce from, for instance, 650 million constraints to 130 million constraints. And now with the new compiler, it takes around 3 hours to do that. Okay, so for we need a good machine. Okay, 64 cores and this amount of RAM memory. In previous versions of the Circom, the one done in JavaScript, this was taking days, okay, of compilation. So it's another, we have to get used of having compilations process that take really long compared to standard languages. So the size of the binary file is like this, okay, so 50 gigabytes but the good point is also that if you have not that many constraints, for instance, 10 million constraints, it can be done in a laptop in a few minutes. Okay, so there is also a good thing. So the point that these simplification techniques cannot introduce new signals and should be efficiently implementable. Okay, and is a new form in the compiler's let's say technology, a new form of code optimization. Okay, so we need to optimize the constraints, and this is a challenging problem. Okay, so we do it for linear constraints, but there are many more things that can be done. Okay, but it's not easy to make it efficiently. So for instance, comparing Circom with Socrates, which is another ZK programming language, we can simplify far more. So in fact, we have used the result of the Socrates, and we were applying our techniques, and we were simplifying again maybe 70% of the constraints in some cases. Okay, so another important thing here is that as a byproduct, we can use this component of Circom as an independent component. Okay, so to simplify the constraints provided by other systems, which I think is a good thing. So if they are given in some R1CS format, we can simplify them. Okay, so here are the conclusion. So the important thing, and what we are proud of, is that Circom is a low-level language. Okay, because I think there is room for a low-level language. Some other languages now are translating to Circom. Okay, because the part of the code which is like a JavaScript code is quite simple, and then you can really write your constraints there. Okay, so explicitly. So it's a nice way to do a higher level language on top of it, because it will provide you the simplification and other good things. So Circom allows the programmer to describe these two things, the circuit by means of constraints, but also the efficient way to compute the witness. And the programmer has full control on the circuit definition. Okay. We also have this Circom lib, which is really important piece of the picture, which many people uses and is happy that there are so many things already implemented. And well, Circom has a large and active community that is helping to produce new circuits that others can use. Okay? Once it is written in Circom, you can reuse it and add it to your programs in Circom as well. And Circom can be combined really to get the proofs and the verifiers with this Snark.js or Wasm Snark or Rapid Snark, depending on in which platform you want to add this ZK protocol. Okay, and finally, just mention this ZK REPL, that is an online environment that for ZK snarks that it's recently built on top of the Circom. Okay, so they just produce Circom and then call to the compiler, and that's it. Thank you.
Thank you, Albert. Great presentation. Very nice, very detailed. Let's go to the next part of the event, which is going to be a panel discussion. And we have two more panelists joining us. We have Daniel Lubarov, who's a co-founder of Polygon Zero, and Nathaniel Masfenian, who's a co-founder of Notebook. I hope they're both here. Right. Yeah, so we have prepared a bunch of questions for the panel, but feel free to discuss whatever you like. One more thing that I want to mention before I forget is that at Delendum, we are also working on building a knowledge base for ZK. And if someone is interested in collaborating, contributing, or providing feedback, please reach out to us. I can post a link to the knowledge base here in the chat. Give me 1 second. Yep, here it is. Okay, so let's get started. The first question we have for the panelists . Right, why do we write new compilers for ZKP programs rather than repurposing existing ones such as LLVM?
Yeah, I think Brian got into this a little bit in his talk. So there are a lot of kind of different performance characteristics between classical machines and something like a ZKVM. For one thing, there's typically no caching layer in a ZKVM. Main memory itself is typically pretty cheap, and it doesn't have any latency. We can just immediately access memory. There's pretty much no latency issues in a ZKVM. And there's some operations like XOR that are very cheap in a classical computer, but not so cheap in a ZKVM. So yeah, I would be interested to hear maybe from Brian or somebody with more experience working with more traditional compiler tools.
Yeah.
Like what are the passes that make sense, and what are where do these traditional tools get in the way?
Yeah, I mean, I think, with LLVM, I think it gets in the way in the sense that it's a lot to learn and a lot to take in if you want to say, get a pipeline going so that, Rust would say compile into Miden. Like that's a pretty heavy lift. So I would say that, it's probably for people's MVPs, it's often just better to do something by hand. Although I think, certainly my opinion is that you should reuse LLVM. And the kind of instances Daniel's talking about are pretty easy to structure, your LLVM compilation pipeline such that you can basically make those optimizations in a really composable and very maintainable way. So I would say, probably people shouldn't be, writing their own compilers. They should be figuring out how to leverage LLVM. Yeah, that's my take.
I think to add to this, I think LLVM also, like in ZK context, would have access to other things like non-determinism, which LLVM doesn't know about. So you'll need to somehow augment it or maybe do something else, because you can, speed up a lot of things using non-deterministic inputs and witness inputs, which, is not something you can do in a traditional hardware machine or a virtual machine executing in traditional software. So there are differences, and it is possible to breach them, but it's I don't think it's an easy thing to say, okay, let's add non-deterministic inputs to LLVM and make sure that works.
I totally agree. Yeah, I think you definitely have to do that in an MLIR context, and you'd have to probably utilize some kind of like hinting that flows down through your AST or something. So yeah, complicated.
I see. Anyone else would like to add to that?
Well, in our case is different because we are not working with a virtual machine in this way. So we are really producing the R1 CS, and then this situation makes not much sense for us. I mean, we could have produced LLVM as a result of the compilation of the computation of the witness, but in this case we decided to do it with WebAssembly, which is more natural in our context, or producing just C, which later on can be compiled into LLVM if you want.
Yeah, I will say that the sort of MLIR gets rid of the assumption that you're ever using the LLVM dialect, which is really the the kind of like Java intermediate form or MLIR or Microsoft IL kind of low-level virtual machine. That particular representation is not really part of MLIR. You can kind of lower from one thing to anything and kind of omit any other thing. So I think it's worth peeking into, just because you can actually take some language that looks like Circom and write a couple table gen files and spit out C, and it's actually quite nice for that purpose. MLIR, because previously obviously you always had to go through the single LLVM dialect, so it's quite a divergence from what people think of as LLVM.
Next question, please. What runtime environments may be prevalent for ZKP in the future, and how does that influence your design choices of compilers?
Yes, I'm not super clear on like what is meant by runtime environments. If that's meant like are we going to execute on CPUs, GPUs, FPGAs, ASICs, and things like that? Then I think over time we'll probably drift toward kind of ASICs. But how long this is going to take, I don't know, because even CPUs are like, you can do finite field arithmetic much faster in a dedicated circuit than you can do on a traditional CPU, right? And with GPUs, you get some acceleration as well. But over time, like, you can really get a lot of performance benefit, which we care a lot in a kind of more tailored kind of hardware environment. And in that case, I mean, it's still going to take a long time to get there. But I do think that it would be interesting how you can kind of take specific virtual machines, for example, a specific like languages that compile down to circle level. Because with virtual machine, for example, yeah, you can reuse some components in hardware, but like there is going to be always something unique. For example, there is something going to be unique to RISC-0, something unique to Maiden, and so forth, that you will need to design a dedicated hardware circuit for. And that would be an interesting, like, you can only do it once something gains a fairly wide adoption. I think it may not make sense to do it for some niche application. So yeah, I think it will drift into hardware over time, but I don't know how exactly long it will take and how exactly it will happen.
And most of the projects that I know, at least, that are working on hardware are focusing on generic operations that don't have that much to do with the language, really, like doing FFTs or doing elliptic, like multiscalar multiplication, or whatever. So they tend to be pretty agnostic to what's going on at the language compiler level. I think for good reason, because we don't know like which of those which approach is really going to be prevalent, and these hardware projects want to make sure they can work with as many projects as possible, because it's really expensive to like develop hardware and stuff, and they don't want to like bet on something that's not going to pan out. So
totally. And I think that you know, if you're thinking of building your own, you know, ZKP system, you know, I would say, I don't know if it's exactly a compiler design choice, but you know, I probably don't bet on one proving system as you're architecting your code. You might regret it later.
Right. 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 Let's go to the next question.
Oh,
if someone wants to, after that, yeah, please.
Well, I just want to reply that I think that's sort of an interesting. I would complicate that a little bit, because if you know, at some point you do need to deploy a system that uses some concrete proof system.
Absolutely.
And you know, maybe if you can move faster by using a particular thing, or if you can make things performant by specializing to a particular thing, you know, I mean, that's why I think sometimes these worse is better approaches win ultimately, because you can move faster, you can get more market share, and then the world will figure itself out around those decisions later.
Definitely. I guess one thing, you know, that keeps me, I don't want to say it keeps me up at night, but, you know, certainly, you know, we're integrating like lookup into our proving system, and it's going to be, you know, 5 or 10 times faster or something like that. And yes, you know, we can do that by rewriting stuff and undoing a bunch of plumbing. But I'll say, you know, the time and effort we've put into trying to keep our prover composable is paying off so far. Maybe the math won't keep changing as much as it has been, but yeah. But also, yeah, getting something to market is important.
Right. This question is interesting. What kind of developer tools should be built next to make building ZKP applications easier, more scalable, and more composable?
And that's a hard one. I think it depends on, like, there's so many different, you know, ZKP in the Cairo or Star, you know, net context is really just a acceleration technique, or a way to, you know, maybe eventually do compute off chain. I guess the prover is not open source. Certainly, you know, the stuff Mina is doing is a really cool, like, easy to use framework for building ZKP applications. But then there's all this sort of applied cryptography knowledge that you kind of need to know. That's something I think about, is like, how do we get developers to understand, you know, what they can do with ZKPs? And to me, it's almost an education problem. I'm not sure what tools are missing now, because I feel like there's such a you know, dearth of understanding of ZK. It's like we're just scratching the surface of the application space. So maybe that's why we focused on just trying to build a very generic system.
Yeah, I think in my mind, like, go ahead.
Sorry, no, just to say that also in this line of adding developing tools, I think that at least there's a group that is pushing for also including what is called formal methods in the development of ZK applications. And this would be good if they can be a side of some of the development tools, such that beginners especially get hints of what they are doing wrong. Because as said, the education is really important, and some people is writing these things and sometimes don't know exactly what they are writing. Okay, so I think it's good if they get some feedback on what is wrong, because otherwise it's not easy. Okay, so after all, if you build a circuit without constraints or whatever thing like this, you don't notice at the time of writing the protocol, but you will see later what happens. Okay, so I think it's very good if there are tools providing this kind of information to developers.
Yeah, I was going to say that, like, in my mind, that the tools that I needed, the tools that basically make ZKPs completely transparent. Like, the end user should not know that they're doing anything with ZKPs. Ideally, I don't know how soon we'll get there, but ideally it should be, you know, I'm just writing this, I have some extra capabilities maybe, but ideally using a familiar language or something not too different from a familiar language. And whether you're using ZKP on the backend, you know, it's kind of like, okay, I know I'm using like there's x86 or ARM is going to be executing the code eventually, but I don't really care that much when I'm writing code at a high level language, what it is. And ARM or x86 is that is going to execute it. So.
Yeah, I think about that a lot in the context of like, I don't know if people have used like proto buffs or any kind of IDL, but you know, if you have a sort of interface for your class, if you can kind of annotate it with, you know, privacy characteristics and stuff, kind of like explain more, you know, from a behavioral standpoint, what the ZKP is doing, so developers can understand that more. That's something I hope we'll see a really good sort of framework for building ZK apps that's more, yeah, descriptive.
Right, absolutely. Yeah. We have only about 7 minutes left here today. So let's go through the remaining questions somewhat faster. This one's interesting too. Do you anticipate ZKVM and ZKP-based systems to become like plug and play components similar to VirtualBox and Docker? And how do we get there?
Yes.
Yeah, it's related to the previous one. So.
Yeah, it's kind of related to the previous one. Yeah.
I think
so. Oh, sorry. Go ahead.
No, go ahead.
I was gonna say, I think like some parts of it will be like for acceleration. I think some parts of it kind of, Brian, what you said made sense about, you know, like there are actually using these things and building some kinds of systems requires other kind of applied cryptography knowledge. You know, like how exactly am I hiding data and so on. That's a little less, that's always I think always going to be kind of application specific. I mean, there will be common patterns that emerge that can be maybe abstracted out, but.
Yeah, I do think that, you know, if you look at something like RISC-0 and you just really want to prove that you ran a particular program that came from, you know, source code that was audited or something like that, then it really does start to look like an SGX sort of virtual machine, but then you don't get any of the cool ZK capabilities. Yeah, exactly.
Yeah, since we are short on time, let's actually try the next one. Can we speed up complex circuits by breaking them down, distributing across nodes in a network, and then composing them back together? And you know, are there other approaches to like handle this type of problem?
Yeah, you can do this.
Yeah,
there are like non-verifiable ways, like this older work of I forget what they called it, but like it's like a paper with like Howard and Osandrikes of like distributed snark proving, and then there's like verifiable ways like using recursion. You can also do this.
Yeah, but I guess that's totally like recursion kind of does kind of magically solves this in a lot of ways. So you can just split a problem up and do the complicated part on a million nodes, and then like build one mega proof and call it a day. Yeah.
Mm-hmm. Is there any other approach to like to dealing with this
besides recursion? I mean, you can kind of, with the ZKVM, you could, you know, write out the state at the end of a particular part of the execution and effectively commit to it, you know, and kind of link things together just by inspection, but it's not as cool as recursion. So.
Mm-hmm. I think
go ahead.
No, go ahead.
So even with recursion, let's say we have a really large Circom program or something like that, and you know the programmer who wrote the code didn't want to break it down into multiple circuits, then it would be interesting to think about doing that in an automated way. And then it's almost like a min-cut problem. How do you divide the circuit into partition the circuit such that there aren't too many connections between between those sets?
Totally. I was kind of taking the like, oh, well, as long as your circuit fits on one machine, you can break the problem down. Yeah. But that's a very ZKVM way of thinking about things. So good point.
I was gonna say that as long as, like, if you're thinking about like distributing across a network of machines, that I think makes a lot of sense to do recursion. I don't know if a lot of other things can compete with recursion because that's like the most special one. The downside is that you still, like, going over the network and doing recursion, you will incur some latency. So if there is a reason for you to like have super low latency, rather than distributing things, going to like FPGA or like some other acceleration on the same machine becomes much more crucial, I think. Because you know, and it depends on the circuit, of course, or a specific program, because in some ways you may not be able to do it. But I think the recursion is great as long as like latency requirements are not like super high.
Right. Cool. Yeah, we are almost at the end here. I think we have one question left, but I also want to mention that we have a Google form to collect feedback from the audience about this event, and a link would be posted here. So please, if you have time, fill out the short survey. Right. So the last question for the panelists, it's kind of a very general question. How do ZKP compilers optimize computation, maybe proof over time, proof size, proof verification, all these things? Very general, yeah.
Yeah, I think that this is one of the parts of I explained. So on one side, you really need to optimize the number of constraints. Again, either if you use this R1 CS or you use Splunk, so there are always ways to try to reduce the size of the proof. And then depending on what you do in R1 CS, it's cleaner. So you reduce the size of the proof and the verification time is constant. But with Splunk, it's important what you introduce, and then maybe you reduce the size of the proof, but you increase the verification time. So there is a lot of also of research there how to do this optimization of the constraints.
Right. So I remember you mentioned that you reduced like 600 million constraints to like 100 million constraints for a certain problem, right? So could you say a bit more about that problem?
Well, in that case, it's just removing linear constraints, which is, I mean, it's something well known. You use Gaussian elimination, but the point here is that you have a really large number of constraints. And in fact, also it's really important to have good heuristics to choose which signal you remove and so on, because depending on what you do, things can blow up. Okay, so it happens that if you choose wrongly the signal to simplify and you do it several times like this, it won't work. So we really work. We need to create clusters. We use we parallelize the process, and this is just for linear simplifications. For instance, in Splunk is even worse because, well, the simplification, the linear simplification will break you the Splunk shape, let's say. And then in Splunk, you also have these custom gates, which, well, it's not easy to decide when to add them or not. And it would be nice to automate all this and have a compiler that at least offers you, would you like to transform this into a custom gate? Because this is used many times, and maybe if there is a way to do it, it would be better, and so on. But it is, well, it will come in the future. We have also tried some nonlinear simplification, but it is another issue because there you really need to simplify only those things that really will not change the behavior of the circuit. So then it's not easy, and make it efficiently is really hard. So I don't really know what to do in this sense.
So Daniel and Co have also done some really cool work on, you know, trading off proof size and time and stuff and combining them with recursion in really cool ways. I don't know if you want to say anything about that, Daniel, but
yeah, I think it's a much easier problem to optimize one property at the expense of the others than just to have a straight optimization, like Albert was talking about, where you just reduce the number of constraints or reduce the witness size. But yeah, if we're willing to trade off, like let's say we're generating kind of the final proof in our ZK rollup that we're going to send to Ethereum, then we really want to shrink it as much as we can, and we are willing to trade off on prover speed for that. So then we crank up the blow up factor to a much larger parameter, and we can kind of adjust the shape of our circuit and adjust the fry configuration in order to optimize proof size.
So a question for Albert. Does Circom kind of optimize for EVM and the Solidity language specifically, or is it verifies?
You might be on mute.
Yeah, I think there's a question for you, Albert. And
yeah,
you
sorry. So
yeah.
I didn't get the question. So I understood you mean optimizing the Solidity code that finally is produced by Snark.js, or what do you mean? Because
yeah,
the problem is that it's a second phase. So we just produce these constraints and the code to generate the witness, okay, in Circom. And then later on, it comes the Snark.js that produces the real proof and the code of the verifier. And in this part, I haven't worked, so I don't know. So maybe we can do something, but at least it isn't related to Circom. So because it will really depend on the size of the constraints in this case. So
Cool. I'm sorry, am I on mute now? Yeah, I don't think we have any more questions here. I don't see anything else on the Telegram chat or on Zoom. So yeah, I think that's a wrap up for us. Thank you so much to all the speakers, the panelists, everyone in the audience for listening. I think it was a great event. I personally learned a lot from it. And we would be organizing more events of this sort centered around zero knowledge in the future. So please stay in touch. If you have any feedback, please use the form to send it to us. And like I said before, there's a zero knowledge, a knowledge base for zero knowledge that we are building, and please contribute to it. Thank you.
Thanks, Shashank.
thank you.
Thank you for having us.
Bye, everyone.
I think you should just call it the zero knowledge base.
Yeah, we need some knowledge to work on zero knowledge.